So yesterday I was making some noise about the setting in which you do differential geometry, right? Spaces on which you can talk of differentiability and so on and so forth. So spaces which locally are Euclidean spaces and so on. So since I have spent some time on saying all those things, I can as well write down a definition and then be done away with it. Okay. So we will not be using this definition. I'm just formalizing something that I was saying yesterday, the proper setting to do differential geometry. Although that's not the setting that we'll be working with, we'll be working on a more down-to-earth setting. So I'm going to write the definition now. So perhaps till the end of the course, we'll not be saying anything more about this. Okay. Hausdorff space. So without this Hausdorff, life becomes uninteresting. So whenever you have a space, unless there are enough continuous functions on the space, there is nothing interesting about the space. So spaces which are not Hausdorff, for example, sequences can converge with several different points and so on, right? So lots of things which are not very pleasant, so to say, right? So most of the times in analysis and geometry, differential geometry, not algebraic geometry, the spaces that you consider will be all Hausdorff. Algebraic geometry, actually the topology, what is called the Zariski topology, is not Hausdorff, although that's the topology that they deal with mostly. Anyway, so which is locally Euclidean. So the following property. So we said around every point there is a neighborhood which is homeomorphic to Euclidean space or ball in Euclidean space. So which means the space itself is covered by such neighborhoods. Around every point there is a neighborhood. So you have a collection of sets which cover the space. Secondly, so for each of those sets you have homeomorphisms of that neighborhood to an open set in Rn. Okay, so you have a collection where these U alphas are open sets in X, and they cover X. So which means around each point there is a U alpha. Phi alpha from U alpha to phi of U alpha, let's say, in Rn, is a homeomorphism of U alpha onto an open set phi U alpha in Rn. So n is a fixed. So this just says that around each point there is a neighborhood which is homeomorphic to an open set in Rn. And then the other condition needed is what I was trying to tell you in the end, how to define smooth maps on such a space, so that the condition that you have to impose some conditions on this, the transition functions or the change of coordinate functions are smooth. So you have, so you can draw a picture there. So this is U alpha, U beta. So there's the intersection there. So you have phi of U alpha here. And then you have phi of U beta. They may phi alpha of U alpha. So we are going to be interested only in the intersection common part. So this is phi alpha there. So this is here. These are homeomorphisms. So the common part here is going to be something here, some part here, some part here. The image of this here, image of this here. So the image of this intersection is this, and is similarly here. So these are all lying in Rn. Okay, so if you start with some point here, for example, you can go back via this, end up here, and then come back here using this map. So in other words, you can go like this. Okay, so what is the map therefore? So this way is phi alpha. So this phi alpha inverse composed with phi beta. So where is this defined? Phi alpha of U alpha intersection U beta. Okay, and ends up in so this everything is inside Rn. So this is an open set in Rn. This is another open set in Rn. What your map does is to take this open set in Rn to an open set in Rn. So the required condition is that this is a smooth function. So phi beta composed with phi alpha inverse is smooth for all alpha and beta. So think of this phi alpha as maps which give you coordinates for points on x, points belonging to x. So if you start with a point here, you look at its image here. So this is in Rn. So if P is this point, so phi alpha P is going to be something here. So you can look at the coordinates of phi alpha P in Rn, right? So we can think of those coordinates of phi alpha P as coordinates of P, right? Via the map phi alpha. So each of these phi alpha give you some, it is a coordinate system in a neighborhood of the point P. But then, of course, different maps, different phi alphas will give you different sets of coordinates. Right? If you're using this, you will end up here. The phi beta of P will have the different set of coordinates. So what this condition is trying to do is to say that going from this set of coordinates to this set of coordinates is a smooth function. Right? So smooth transition from one set of coordinates to another set of coordinates. So these maps like this are called change of coordinate maps or transition maps. Transition from one set of coordinates to another set of coordinates. So these transition maps or change of coordinates map. These are smooth. That's the assumption. So once you assume this, as I mentioned yesterday, you can define, if you want to talk about smoothness of a real valued function here, you can compose with this and look at the corresponding function from a subset in Rn to R. So we know what is meant by smooth there. So you say that f is smooth provided this composed with f is smooth. What this condition, this assumption does is to show that the concept is well defined. It's not going to depend on phi alpha. If you use phi beta, that is f is smooth with respect to this set of coordinates if and only if it is smooth with respect to this set of coordinates. So it's not going to depend on the choice of coordinates that you make. So for that, you need this smoothness of the transition functions. So a space equipped with all this structure, so these are, each of these u alpha phi alpha pair, these are called coordinate charts. Each u alpha phi alpha is called a coordinate chart because each of that gives you a set of coordinates or points in u alpha. The collection of all these coordinate charts is usually referred to as an atlas. The collection u alpha phi alpha. So you have a collection of coordinate charts which cover the whole space, so that all change of coordinate maps are, so that's the setting that you have. So once you have all this gadgets appended to the space X, so you have what is called, so then you call X as a, X is called a smooth manifold. Smooth because we are assuming that all the functions involved are smooth. If you are looking at maps which are CK, so then you call it as a CK manifold and so on. Okay. Anyway, it doesn't matter. So these manifolds are spaces on which we can talk of differentiability. So once you can talk of differentiability, you can try to develop some differential geometry on such spaces. Okay. Of course, for talking about other things like geometric concepts like lengths of curves and curvature and such things, you need more structure, just like you have inner products on the Euclidean space. So on each tangent space of your space, you need some inner product. So as I mentioned yesterday again, so this is what is called a Riemannian structure or a Riemannian metric. So manifolds together with a Riemannian metric. They are called Riemannian manifolds. So proper geometry in that sense are geometry. So you can talk of all your geometric concepts that you come across in Euclidean setting. You can talk about them in the setting of Riemannian manifolds. So we get what is called Riemannian geometry. Right? So we will not, maybe towards the end of the course we will say probably something, at least mention Riemannian metrics and on surfaces, but not in the abstract setting. So then you have Riemannian manifold. So these are manifolds plus so in a way these Riemannian manifolds are the proper setting for doing differential geometry. But we are going to work completely in the Euclidean setting. So the manifolds that we are going to look at are all submanifolds of Euclidean space. Not only that, we are going to simplify things further by looking only at hyper submanifolds or hyper surfaces. So surfaces which have codimension 1 in the ambient space. In Rn plus 1 or in R3, we are going to look at only two surfaces, two-dimensional surfaces. In Rn plus 1, we are going to look at only n-dimensional surfaces. So this makes life easier again when you want to talk about normal vector fields and orientation and such things. So you don't have to do, essentially you don't have to do anything. You already have, once you have an n-dimensional subspace of an n plus 1 dimensional vector space, you already have the concept of a normal there. Right? Just like you have in R3, you have normal to a plane at a given point, right? So you can talk of normal to a hyper subspace in Rn plus 1. So it's just the orthogonal complement, if you like, of the n-dimensional subspace. That is going to be normal because you have already an inner product in Euclidean spaces, so that makes things simple. So you don't have to introduce a new structure which gives you these inner products. You already have a natural inner product, so everything sits inside your Euclidean space. So that is what we are going to make use of. That simplifies everything a lot. Okay, so in practice, when you look at surfaces, our surfaces, so here the thing is you are starting with an abstract space and trying to put some coordinates into the space. But what we are going to do is we are not going to start in an abstract space. We are going to look at Euclidean space. Okay, so we already have everything there. Only thing is we have to see how your surface sits inside the Euclidean space. So in the abstract setting, so you have to, what do? You start, so you are starting with the space, right? So you are trying to give coordinates to points on the space. But now we are going to be in the Euclidean setting, so we already have coordinates here. Okay. The only thing is how do you take over these coordinates in the Euclidean space to coordinates on the surface. That's all. So in practice, in our setting, we actually will be going in the opposite direction. In the sense that Here you are starting the space and then looking at patches in the space going to the Euclidean space. Our surfaces are all going to lie in some Euclidean space, right? So let us say a surface in R2, R3, for example, a two-dimensional surface. So if you are looking at this picture, let us say you start the sphere, for example, then what does this do? If you want to show that sphere is a manifold in this sense, what you have to do is you start with points on the sphere and find a neighborhood of the point and find homeomorphisms of that neighborhood into a subset of the plane. Right? That's what this does. R2. Dimension is 2 now. So each point has a neighborhood which is homomorphic to a disk in R2. That's it. In this setting, that's what you are going to do. But when you work with surfaces, actually, we are going to go the other way. Start with patches in R2 and take them to patches on the sphere. Right? That's how it's usually done when you work concretely in surfaces. So this is a patch in R2 mapped to a patch on the surface patch, as they call it, or chart on the surface. So as I mentioned yesterday, there are different ways of defining a surface. One is like this, going the other way. You start with something in Rn plus 1 and give maps from open sets in Rn to parts of the surface, patches on the surface. The other one is to look at surfaces as level surfaces. Okay, just like sphere equation, you write x squared plus y squared plus z squared equal to 1. So that is a form f of x, y, z equal to 1 by suitable function f. So these are what are called level surfaces. So the definition that we gave yesterday was of a level surface. That's going to be our definition of a surface. And n surface, this we wrote down yesterday, I'm writing down again, S in Rn plus 1 is a level set of the form S equal to F inverse C. So this means all points x, y, z which are mapped to C by the function f, where f U is an open set in Rn, and f is a smooth map from U to R, real valued function on this open set. So this S is the set of all points which are mapped to set of all points in U which are mapped to the constant C. Okay. So this way, so that is not all, because you have to have some condition to make things smooth, right? So everything, for example, if you take a constant function, right? Everything is going to be 0. So you want some kind of regularity, which means that some partial derivative at least is non-zero. a smooth function such that the gradient is non-zero at every point of S. This just means that at least one of the partial derivatives is non-zero at each point of the surface. So this is what is called the regularity condition. Any point P with this condition is called a regular point for the function. We want every point of the surface to be a regular point. So this is going to be our working definition. So what is the other possible definition in terms of charts? The surface is covered by coordinate patches. So what is a coordinate patch? You have an open set in R2, or in this case in general for n surfaces in Rn, and a map from smooth map from that open set to R plus 1. This is what is usually referred to as a parametrized surface, right? So just one parameterization may not cover the whole of the surface, so you need to have several patches of this parameterization if you want to cover the whole thing. The parametrized n surface in Rn plus 1 is smooth map, let's say phi Basically, you want to land up on the surface, right? But smoothness on the surface, so smooth map phi such that you have to specify the point now. So P, when you, okay, so this is just defined as a map, but as subsets of Rn plus 1. So what do you have? So what is called a parameterized surface here is a map, but actually the surface is the image of this map in Rn. Okay, so if you think of the surface as S, if you take a point in S, a neighborhood of the point in S is got by taking a neighborhood in the whole space intersected with S. So this is going to be of the form S intersected with. That means open in Rn plus 4. Just like you see, how do you define usually a curve? A parameterized curve is a map, right? So, but when you think of a curve, you don't think of a map, but the image of that. So it's the same thing here. So what is not any smooth map? Again, you need some condition. You look at the derivative of the function. Okay, or if you like the Jacobian matrix of the function at the point P. So what is this now? So this is a linear map. So this is in Rn. Okay. So this is in Rn. It goes into Rn plus 1. So the derivative is going to be a linear map from Rn to Rn plus 1. What is the possible dimension of the range? Or in other words, what can you say about the rank of this map or the Jacobian matrix there? n to n plus 1. So at most it is n, right? It has to be less than or equal to n. So what you want here is the maximal rank. You want this to be of rank n. That means the image is an n-dimensional subspace of Rn plus 1. So if you want to fit this into our definition earlier, this gives you only one patch. This may not cover the entire surface. So this gives you only a patch on the surface. So you have to cover the surface by patches like this. So if S is covered by patches like this, then you call it as a surface, a smooth surface. But in your this thing, only this much is given. So textbook. The point is, of course, it does not matter whether you start with this definition, a surface as a level surface or as a parametrized surface. It doesn't matter, they are equivalent. In what sense? Every level surface is a parametrized surface, and conversely, every parametrized surface is a level surface. All this locally, may not be globally. Right? Because we are interested only in differentiation. Locally, if it is fine, it's fine for us. Okay? So, the two definitions, that is, an n surface is locally a parametrized surface, and conversely, a parametrized n surface is a level surface, is an n surface, in this sense, a level surface. Okay. How do you get that? Inverse functions here, both cases, both this way and this way. So I will probably try to give a proof of one of these implications at least. Okay, right now. For the other implication, we will need some more things to come. But in the meanwhile, let us look at some examples. Okay. So level surfaces are some of the most common ones that you come across, right? You just write some equations. By putting something here. Here also you can put the same thing if you want. Okay, let us, before I give list more things, let us see what these are. First one is familiar, the sphere in R2. So all these are examples of two surfaces in R3. Okay. Of course, before you say that, you have to check that regularity condition. Okay, so if you look at this, for example, the partial derivatives are 2x, 2y, 2z. Right? Not all of them can be 0 on the sphere because the sum of the squares have to be 1. So the regularity condition is satisfied at all points of the sphere. What is this? We are in R3. Okay. Don't say it is a circle. So if you want, we will come back to this. Go to the other thing. Okay, Z illadanaala you think of this as a circle. So So we will come back to that. So what about this? What is this? Haven't you studied three-dimensional coordinate geometry somewhere? Analytical geometry? These are all quadric. What are these things? These are hyperboloids, right? One hyperboloid of one-sheeted hyperboloid, two-sheeted hyperboloid. Which one is one-sheeted? Which one is two-sheeted? So what is meant by one-sheeted and two-sheeted? One-sheeted hyperboloid is connected, right? Two-sheeted hyperboloid not connected. It has two connected components. One like this, the other like this, right? This is a two-sheeted. This is a one-sheeted hyperboloid here, which is, if you know what this is, we call it moda. I don't know what you call it. The seat, the one shaped like that, with a seat like here, right? Must have seen it. I don't know what you call it. We call it moda. So that's an example of a one-sheeted hyperboloid. Okay. So you have one piece. See the one-sheeted hyperboloid. Inside there is a cone, and inside there is the hyperboloid of two sheets. One. So this sheet is the upper one. There is similarly a lower one. So this is a cut here to show what is inside this picture. If you look at this one-sheeted hyperboloid, if you know what that thing is, it's made of paramgu. Yeah. So these are all straight lines. So the surface is entirely made of straight lines. So what is called a ruled surface. So each one is a generator like that. If you take one of them and rotate suitably. Yeah, so this is another version of the last one. The other the one on the right hand side. So just look at the plane sections of this, right? So if you cut the sphere by planes, you are going to get circles, right? If you are going to cut this, for example, if z is a constant, plane z equal to constant, you are going to get a circle. On the other hand, if you cut it by a plane, say x is equal to constant, you are going to get a hyperbola, y square minus z square equal to something, right? Similarly here, so this will this will not pass through the origin, okay? So this is obviously a two-sheeted hyperbola. So this will be some portion up and some portion down. There is gap between. So you try to look at sections like this, horizontal sections, that is sections by planes parallel to the z-axis, parallel to the xy plane, parallel to the yz plane, parallel to the zx plane. So, okay. So each will give you a conic. So this picture just shows you again a hyperboloid, but now the equation of the hyperboloid is xy equal to constant. Xy equal to constant gives you a hyperbola whose asymptotes are the axis. Rectangular hyperbolas. So this is one-sheeted hyperboloid. Two-sheeted hyperboloid. coming back to this, see, z equal to constant gives you hyperbolas. What about the other ones? X equal to constant or y equal to constant will give you y square equal to some constant times z, the parabola, the yz plane, right? So the sections of these are either two of these coordinate sections will give you parabolas, the one will give you, other one will give you the hyperbolas. So this is what is called a hyperbolic paraboloid. The same way, this is an elliptic paraboloid. Because when you take A equal to B, you get circular parabolas of revolution. Usually, if you look at antennas, in these days, what is it called? The dish, this thing that you have on top, right? Dish TV, when you get whatever connection you have, you will have some dish on top. So those dishes are shaped like a paraboloid, right? Usually elliptic paraboloid. And even you might have seen, at least in pictures, telescopes, right? Large dishes they will have. So those are all paraboloids only. Even at home, even if you look at TV, you will have, what is it called? In Tamil we call muram. So which you use to the grains, right? Like this. So that is an elliptic paraboloid. See, the back portion is essentially an ellipse. This section is a paraboloid. The surface on which you actually have the grains, it's shaped like this, right? So if you cut parallel to that, you are going to get parabolas. So that is an example of an elliptic parabola. I don't know, I'll picture the monkey saddle cover again. So this is what is called a monkey saddle. It's an example of surface with negative curvature at least some point. Why is it called monkey saddle? So you know what is meant by a saddle, right? For example, if you want to ride a horse, you put something on that, some kind of seat on the horse and then sit. Shaped something like this, right? So on that, on either side, you will have some curved surface like this. So on which your legs will rest. Okay? Some dent like this on both sides. So you need two like that. But for a monkey, it also needs one for the tail. Okay, so on this surface there are three things like that. Okay, so that's why it's called a monkey saddle. But there are other kind of surfaces that you also familiar with, what are called surfaces of revolution. Of course, these come in the other category usually, surfaces of revolution. But what are they? as the name suggests, you take some curve, take a line which doesn't cut the curve and rotate the curve around that line, right? So this is y, z, x. Okay. So the board of the plane is a yz plane. The x-axis is perpendicular to the board. Okay. So you take some curve in the yz plane and rotate it about the z-axis. So what will you get? What will happen? For example, if you take a point here and rotate around the z-axis, you are going to get a circle like this. A circle whose radius is this distance here. So this happens for each point. So we get a surface like this. It goes this way. So we have a picture here. So each point on the curve makes a circle with center on the z-axis. Radius equal to the distance of the point from the z-axis. Right? So we get a surface of revolution. An important example is the torus. Torus of revolution. So you take a circle the yz plane like this. Rotate this about the z-axis. What is the picture that you will get? So this will give you a circle like this. This will give you a circle like that. So this will give you the largest circle. Okay. So there is a picture of the torus there. You will have something like that. Yeah. So there will be another picture which shows the axis and rotation. So you will have a picture like this. You have it? Yeah. Okay. See, the important things to be noted are circles given by this point, and the furthest point here. Okay. The nearest point and the topmost point and the bottommost point. The four circles. So this give you the nearest point will give you the inner circle there. And the farthest point will give you the largest circle. And these 2 points, so if you think of this as resting like this, play, ring or whatever, so the point of the contact between the torus and the plane will be a circle. Right? Similarly, on the other side, there will be a circle. So those are the circles here. This top circle, topmost circle of the torus. Similarly, the bottommost circle of the torus. So essentially what these two circles do, when we come to curvature, we come back to this. So these two circles, the topmost circle and the bottom circle, essentially divide the torus into three distinct regions. One, the inner region, right, which lie inside the, and the other, the outer one, and of course the one is the circles themselves, the two circles themselves. See, if a point outside the surface curves like this, so you have positive curvature. So inside the hole there, the surface curves like this. So points there have negative curvature. And points on these two circles have zero curvature. Right? So on the torus, you have all three kinds of points. So these are what are called the hyperbolic, elliptic, and parabolic points. Hyperbolic points are those which where the curvature is negative. Elliptic means positive curvature. Parabolic means zero curvature.